So good afternoon, everybody. This is our March Flight Mechanics TDT meeting. And as you see, we're going to have Rob Fal talk to us today about OpenMDAO, and we're going to record it for the Academy. So our normal team meeting status and center news will be handled after this talk. So Rob, if you're ready, I'll let you begin the presentation, and thank you for doing this today.
No problem. Thanks for having me. So I'm going to talk to you about OpenMDAO. I guess you can think of it as an optimization framework that we've been developing at Glenn Research Center with partners across the agency and across academia and industry since about 2008 or 2009, I believe. I came into the project around 2018, so my experience is a little more recent. The motivation behind what OpenMDAO does is that as systems analysts, we want to get more reliable solutions earlier in the design and analysis process. So my colleague, Christopher Lupp from AFRL, we had a workshop for OpenMDAO in the fall, and he presented a chart like this, and I think it really succinctly sums up the issue of like, in general, it's really easy to get low fidelity analysis early on, put huge error bars on that, and then even then, you know, by the time you start applying realism, you might essentially break your feasibility. So we want to move that blue curve up into that we have higher confidence earlier in the process. We want to utilize higher fidelity models earlier in the process, reduce the time required to set up the analysis, and reduce the time required to perform the analysis. This is another chart that kind of highlights the issue of you have in your computational costs. For low computational cost, MDO has been demonstrated with a good number of disciplines, but those disciplines are generally low fidelity and have been tackled via either finite difference derivatives. When we're talking about optimizing system models that use these low fidelity models, we're using either finite difference methods to get derivatives across the model of the outputs with respect to the inputs, or gradient free approaches like genetic algorithms or things like that. Alternatively, in the high fidelity realm, things like CFD and FEA, there are fidelity models there, but they so computationally expensive. So what we're trying to do with OpenMDAO is bridge that gap and allow us to do higher fidelity optimization at lower computational cost and sort of, you know, bridge these two islands. In order to do that, OpenMDAO has focused on applying gradient-based optimization as part of the MDO as a part of the MDO process, part of the multidisciplinary optimization process. When we talk about applying gradient-based optimization, we do that because it tends to be orders of magnitude faster than gradient-free methods, especially once your number of design variables gets anywhere near. And it's faster than finite difference. So this is a plot out of an early publication of ours, where, you know, legacy tools like the Otis trajectory optimization tool that I use, it uses finite differencing and it does a great job. But if we could apply analytic derivatives, get our derivatives more accurate and get those derivatives more quickly, we could really make gains in how fast we could perform analysis. So then when you're out computing the derivatives, and there are a few equations in this slide and the next, and those are the only two equations in the whole presentation, I promise. But basically, talk about chaining together what we would call this. You might have discipline A, B, and C chained together, you know, so that my input of my model takes some input X, and at the end of the day, I'm worried about minimizing or constraining some output F. And if things just flow one to the next, that's the calculus chain rule. We know how to do that. That's pretty simple. But as soon as we introduce a feedback, that gets a little hairier. And basically this involves something called adjoints. And usually when people hear adjoints, they get scared, but OpenMDAO was basically built to make this part of things not scary. And this is really relevant, here at the Flight Mechanics TDT, because when we're talking trajectory optimization and orbital mechanics, we're talking about a lot of implicit models in our systems, things like solving Lagrange's equation for orbital mechanics, solving Kepler's equation, figuring out your geocentric latitude. All of these things are implicit calculations, and in order to get accurate derivatives across that, finite differencing is really easy to break. It's really fragile when it's trying to finite difference across something that's using a non. You can set up those systems in such a way that you can accurately get the derivatives, but if you're implementing that on your own, things get really hairy really fast. And in the real world, we tend to have systems where models can contain nested models, and it's solvers all the way down. It's nonlinear solvers like Newton solvers all the way down. If you're doing something like that and you're trying to roll your own approach, good luck is basically what we like to say. So OpenMDAO was developed to enable the calculation of accurate derivatives across complex models that can be arbitrarily complex. No matter the level of nested solvers, no matter the level of feedback, we can get accurate derivatives, and then we can do interesting things with those derivatives. So OpenMDAO's contract with, if the user writes what we call a component, essentially a kernel of a calculation for OpenMDAO, and they can choose a way to get derivatives across that. They can use finite difference across that component just by that component on its own. They can use complex step, which is sort of similar to finite differencing, but it gives more accurate results across that component. They can use automatic differentiation, and with the recent growth of the machine learning community, there's a lot of interest in that. Or they can do the derivatives by hand, compute the derivatives by hand, and provide those to OpenMDAO. And no matter how complex each little piece has these derivatives across it, OpenMDAO will give them the total derivatives across their model. It's essentially chain ruling together, if you remember from high school calculus. What those are, except as I've kind of explained earlier, the chain rule really breaks down when you get into feedback, and that's why we need these more clever approaches. So once it does that, it gives you these total derivatives. Then OpenMDAO can use those total derivatives to either drive nonlinear solvers like Newton's method, remove the residuals with that, and solve equations like Kepler's problem for you, or based optimization drivers like SNOpt, IPOpt, SLSQP, et cetera, to solve optimization problems using those. So I've talked a lot about what it does. How it does it is it's essentially a Python API. And a lot of times I think people think of their problem structure in OpenMDAO sort of like a system in Simulink, except instead of defining a simulation, calculations. And that order of calculations can be based on a few things. You can have components of a calculation. Those calculation components can be grouped into larger groups to kind of like hide that complexity. And then you apply connections and say, this output from this calculation needs to be an input for this calculation. You can tie solvers to one or more groups in your model. And then those are nonlinear solvers like Newton's method or Gauss-Seidel to actually converge a system, or linear solvers. Linear solvers are sort of under the hood, but their job is to compute our derivatives for us in OpenMDAO. And then you take that entire model and you can couple it to an optimization driver like SLSQP, IPOpt, or SNOpt. And you can tell OpenMDAO, this is my objective, these are my constraints, these are my design variables, go, and it will run the optimization for you. So that kind of in a nutshell is how OpenMDAO works. If you want more details, there's a lot of math behind it. It's the techniques that are used within OpenMDAO were kind of developed around 2010 to 2015 by Akeem Martins and John Wong at the University of Michigan. So they have some publications on the math that we're using there. And there's been a lot of development by the OpenMDAO team to basically take that theoretical mathematical framework and turn it into an API, a Python API that can be used by engineers. So OpenMDAO is a foundation for other tools. So we have this base capability where, you know, we can provide models and it can give us derivatives and help us attach optimization capability to things. We have OpenMDAO based tools that we put on top of that. Some of the more popular ones that we help develop at Glenn are Dymos, which is a trajectory optimization tool, PyCycle, which is essentially a propulsion analysis, propulsion cycle analysis code, and Aviary, which is an agency-wide developed draft analysis tool. As far as what some of the notable use cases of OpenMDAO have been, one of the first indications that we had a pretty good idea was when they essentially NPSS, the National System Software, I believe is the acronym there, which is engine cycle analysis code written in C++. And they essentially build it from the ground up in an OpenMDAO architecture. So instead of being in C++, this was all Python. And then they did an optimization across this tool to try to optimize system for a vehicle. And being Python, it's unsurprisingly slower than MPSS when you do a single analysis. But the optimization in OpenMDAO are so much more efficient a code like NPSS that it's far faster when you. We've been trying to push our boundaries into higher fidelity modeling. So Justin Gray, in getting his PhD at the University of Michigan, applied OpenMDAO to complete a aeropropulsive design optimization, where he was taking something like the Stark-Able concept with a tail cone thruster and designing what that tail cone thruster should look like, propulsion characteristics, and be appropriate as far as the aerodynamic coefficients, characteristics of it go. So that's another kind of notable use case. And then as far as one of our use cases, the University of Michigan have produced several tools. One of them is called Open Concept, which is sort of a low craft optimization code for, I believe at the time I was aware of it, it's for conventional takeoff and landing aircraft, but it could look at things like hybrid electric architectures and things like that. All right. Another use case that I like to point out, just because it's really outside of my wheelhouse, and I think it's an interesting use case, was a paper on the fusion energy side, where people developed a fusion reactor, a tokamak reactor analysis and optimization tool based on OpenMDAO. So there are other use cases that we have. Wind energy is very popular right now. A lot of use cases, especially in aircraft of flight, seem to be driving most of our industry and academic use cases right now. So I mentioned earlier Dymos, which is a trajectory optimization tool built in OpenMDAO. It's Otis inspired, so anybody here who has used Otis in the past will kind of recognize it. Could make sense of the input files for it. So it's built on top of both pseudo-spectral methods and shooting methods, akin to what Otis had. It uses analytic derivatives for more robust convergence, typically, than we would see in Otis. As far as features that would be familiar to Otis users, it's still based on phases, breaking a trajectory into phases, applying boundary and path constraints to those phases. There's still the notion of parameters and controls and states. Some of the newer features we have are the notion of trajectories, so that the trajectory of a vehicle in Dymos is no longer necessarily the top of our optimization problem. We might be designing a complex system and have that complex system design be one box in diagrams I was showing you earlier, and then aside of it and the trajectory behavior. And so it's for something like a control or a system, we have the ability to make a trajectory no longer the top of the model like it had to be in Otis. There are polynomial controls which let the user force lower order control behavior on their system, which is useful when users it's common for users and tools like Otis to try tool to solve an optimization problem that maybe isn't posed as well as it should be, and sometimes the controls don't really matter and things like that. And forcing the ability to use lower order controls, polynomial controls, really helps convergence there. And then because it's built on top of OpenMDAO, we sort of get its optimization suite for free. So we can couple the tools not only like SNOpt like we currently do, but IPOpt and PAROpt, which are some newer but similar trajectory optimizer capabilities. Other things that we've pushed the envelope with, that our trajectory no longer has to be the top level of the optimization problem. And because of that, it gets difficult. Sparsity pattern of the derivatives is, and the sparsity pattern really means that I have those form the rows of these matrices that you're looking at here. Those are the things coming out of the analysis that we're training or minimizing, and they're impacted by our design variables, which are represented by the columns here. And Otis was pretty good at applying a method called sparse finite differencing to only compute, call the model, evaluate the model as much as it needed to accurately and efficiently compute those derivatives. But now that we've introduced potentially sibling analysis aside the trajectory, we might have a case where we have a trajectory, we've got a typical pseudospectral sparsity pattern like you'd see on the left here, and then now we have this dense row, which would typically really kind of obliterate the efficiency of Otis. This would mean that our entire trajectory is impacting some constraint or objective later on. So if you took a trajectory output by a trajectory optimizer and gave it to something like an acoustic analysis tool, and that acoustic analysis tool looked at the entirety of that trajectory and gave it some sort of score, tried to quantify the acoustic behavior of it with a score, and then you tried to limit of thing we're talking about here, where one output of the analysis is sort of dependent on all of the inputs. Because of the derivative coloring algorithms that we implemented because of Dymos, we can now really efficiently get derivatives across even that sort of system, which is something that we couldn't do before. And then this is a chart from a paper on Dymos a few years ago, and it's just trying to highlight that when small problems, Otis, but as we increase the size of that problem, the more efficient techniques involved in OpenMDAO and Dymos, despite the fact that it's running on an inherently slower programming language like Python, it starts to perform, as well, and then eventually overtakes Otis and its capability. And then typical pseudospectral methods, but OpenMDAO can do things like reverse differentiation, so that if I only have a few outputs, it's essentially a more efficient way of computing derivatives when I have few outputs but many inputs, as is the case trying to employ a shooting method. You have a lot of control variables that potentially impact that trajectory, and only an objective or some boundary constraint at the end. That's like a case that highlights the utility of reverse differentiation. So Dymos right now is being used in the industry for novel aircraft concept development and launch vehicle development. A lot of our industry partners ask that I not call them out as to what they consider a trade secret. We're also being used at NASA to develop the next generation of aircraft sizing tools based on legacy tools, FLOPS and GASP. Dymos is also being used in academia due to the fact that it's open source. It's really easy to get out apply it and learn it. Unlike Otis, it does not include high fidelity equations of motion. So the use physics models to use Dymos, but we really strongly believe in delivering open source software. So that's the paradigm that we're sticking with. This I brought up as just kind of one interesting use case of Dymos, kind of another one that kind of outside of my wheelhouse, but this was done by a student at the University of Michigan who I believe now has a career in the Formula One racing arena. And this was lap time minimization using Dymos across he had modeled several realistic racetracks. He's modeling things like the down angle on the wing on the back of the race car. It's a four-wheel drive race car, so he's modeling the torque and the traction applied to each wheel. And some of these models are over 1,000 segments, so we're talking like huge models here. And getting, despite the fact that this is applying it to like a Formula One race car and not a spacecraft, this is really complex, difficult trajectory optimization being done here. So as far as DAO, I've mentioned a few times that we're developing the next generation of NASA's standard aircraft sizing software. One of that is called Aviary. It is being built to replace legacy tool agency like flops and leaps. The reason that we're going through this endeavor is because those legacy tools aren't really capable of powertrain electrification, eVTOL, and an alternative fuel studies that the agency is really interested in looking at right now. We're also looking to really tightly couple the integration of the aircraft design with high fidelity analysis, like things coming out of PyCycle, which, if you recall, is the NPSS clone built on top of OpenMDAO. MFIS is a high fidelity application of OpenMDAO that's really looking to take high fidelity tools, mostly CFD and FEA tools, Fun3D, Cart3D, VSP Aero, ADFO, DA Foam, and SU2, and it's taking those and it's making it so it's easy to couple those tools with OpenMDAO. One of the things that we're constantly struggling with in OpenMDAO is we provide really good capability and expand the state of the art, and then users basically completely expand to take up that capability to the point where the difficult part is no longer the fundamental math involved. Now the difficult part is just the complexity of the models and how to efficiently apply those within OpenMDAO without it being an expensive process every time. So that's really what this effort is about. It has a lot of partners across NASA and academia and a few industry partners as well. NASA has undertaken the model-based systems analysis and engineering working group, which is basically targeting new capabilities and of leveraging legacy combination with modern architectures and performing state-of-the-art coupled optimization. So that's something that the funder of OpenMDAO, which is ARMD's Transformational Tools and Technologies, they're working with groups like EPFD to kind of find places where they can all find common. One of my colleagues, Kaushik Panapali, is working with several folks under Stephen Edwards at NASA Marshall, and they're coming up with a dynamic rocket equation tool that is basically a space mission architecture optimization tool. So when we're talking about Earth to Moon to Mars, they're developing a tool that can really figure out, what's the right combination, what vehicles do I need to send up and when in order to make such an architecture minimize its cost. And then we have other ongoing developments, acoustic analysis and optimization based on that, so that we can quantify aircraft acoustics with open source tools. uncertainty quantification and robust design, interfacing with FEA tools like TAX for analysis of composite structures, and OpenVSP and VSP Aero for CFD analysis. As far as the relevance to the tools produced by this community, I would really love it if we basically made more NASA tools capable of living in this MDAO environment, be that for OpenMDAO. But the crux of that is, we should work so that our future software tools provide derivatives across their models, and if those models are too complex to do so, exposure OpenMDAO will provide the solvers. So, for instance, if you had something, a tool like Copernicus or Asset, it'd be great if we could just tie to that. We don't want to write a new tool, a new set of dynamics, and something that we have to validate over again. But if we can leverage those existing tools and make them part of an MDO process, I think that would be, a really kind of the best of both worlds there. And then as far as tips for other things, provide in-memory APIs when possible, because we do talk to some tools with by writing input files for them, calling them, and then reading the output files, and it's just orders of magnitude slower than we could do it if we had so-called in-memory APIs where that tool is just kind of sitting there and waiting for us to essentially communicate with it and ask for analysis to be run. And then in doing all of this, there's a lot of overlap right now between the methods involved in multidisciplinary optimization and machine learning. And so by undertaking processes like these and getting models that are differentiable, that allows us not only to play in the realm of MDAO, but also with machine learning applications, since those machine learning applications are so dependent on getting accurate derivatives as well. So I have a whole listing of software packages that are kind of in the same family as OpenMDAO. Some of them I've mentioned here, some I have not, but I will add this provide a file so that everyone can look to see what's available here. And then as far as relevant documentation, so I have that for several of our bigger projects, and then a link to our YouTube channel where we have videos on what we call our practical MDO training course, which kind of gives people an introduction to how to think about modeling things in order to work within an MDO environment. And then presentations from the workshop we had in the fall, where we had several dozen people come on site at Glenn from the internet and talk about MDO capability in the future. I think with that, I will take any questions you have.
Hey, Rob, this is Heather. So talk to me a little bit about the software usage agreement process. I know these are open source, but previously on a slide, you had mentioned that one of the versions of the packages didn't have like the equations of motion, so users had to provide their own physics. Are each of these kind of limited in some way in capability? Is it clear what the user has to be able to provide or is not getting access to? And what is your legal, do you require like a contract or a usage agreement has to be signed for each of these?
We do not. They are completely open source. They are used in the national community. We have a ton of users in Europe. And, like going into Dymos, we just go in with the assumption that, we are not going to in any way push the boundary of where we might trigger export control restrictions. So it's all distributed with the understanding of, here's a really strong capability as far as trajectory optimization goes, but it's on you to provide the physics there. We have looked at Glenn at kind of starting to mimic the higher fidelity physics in Otis, but to this point, we have just been so busy on other projects that hasn't been a priority. And so that capability is sort of sitting there in a nascent state, but it's nowhere ready to be distributed itself. I could see potentially in the future, us saying, look, here's Dymos and it's open source. but here's a separate software release that gives you higher fidelity capability out of the box, but then that's subject to export control and the license agreements that go along with that.
So if the user community kind of identifies a bug or a feature that they want repaired or inserted, how does that take priority? I mean, are you looking at a year-long waiting list, or how do those issues get raised?
So in general, we have two development priorities. One are for NASA projects, and those are in general our development priority. Needs this capability or found this bug, please fix it, and that bumps it up to the top of the list. We have a full-time development team right now of a couple of civil servants and a few contractors who basically are always available and still continuously developing on the code. Bug fixes take precedence when found, especially if it's something that's blocking someone's work. So even if that's coming from an external user, if it's something that we can knock out in a short time frame, we usually bump that up in priority, and that means it gets fixed in a day. As far as what's living, our GitHub repo at github.com. And then we try every month or two or so to perform a release so that, if you're a Python user and, you can do something, and that will go out and find OpenMDAO's latest version and install it. Those versions get updated about once a month. So that's the frequency at which we're looking at. I had a user of Dymos this morning on a NASA internal project say, oh, hey, I think I found a bug, and I think we had to fix up within 45 minutes or so for that one. So we have a pretty fast turnaround time.
Okay. No, this is great. And so, I really like that you're kind of recommending or encouraging the community to look at their tools, their center tools, to see how we can, maybe even expand on our flight mechanic tools interoperability study or this is a follow-on, potential assessment to link those together, right? Like you mentioned, Asset or Copernicus to take advantage of the capabilities. So I'd like to maybe put that in the waiting room and think about how we can work with the other centers to fuse those together.
Okay. And I do have an intern who's looking at kind of coupling OpenMDAO to Copernicus right now, but that's done with the understanding that we can't get to doesn't provide some of the things we want. So that kind of limits how we get derivatives from it. We have to finite difference it, which isn't necessarily ideal. But we're at least starting that capability so that it'll be something to build upon.
Do we have any other questions from our TDT membership?
I've actually got two questions. Hey, Rob, it's Aaron from Marshall.
Hey.
One thing I'm curious of, looking at trying to integrate it with Copernicus, I've been trying to play something similar with Asset, and Copernicus not having analytical gradients really kills an optimization process. Have you looked at any type of way to just basically solve the problem in OpenMDAO and then port the solution into Copernicus?
Not yet, because I feel like as soon as I do that, then we're talking about an effort to validate all of the math that goes into and the ephemeris and there's so much complexity in my experience in something like Copernicus or Set that's not something that I have the bandwidth to undertake right now to try to solve. I mean, it's I know being built on Fortran, Copernicus could potentially make use of something like complex step. But I suspect that, I don't know how many calculations in there are essentially not available to complex step, non-analytic functions and things. The ephemeris coming from NAIF spice tools are, notoriously, it would be great if they would usually resort to things like, well, let's, fit a polynomial to that, and then we'll get the derivatives that way. That's, and a couple times I've mentioned to Jacob Williams, it'd be great if we could do things like this, but it's just a matter of priority, and it's not necessarily something, people are very good at making use of the tools they have. And to the point where I see people, encounter bugs in OpenMDAO and Dymos, and they just work around them and they don't tell me about them. And I'm like, no, you need to tell me about these and I'll fix that bug. But, we live in a community that's just really good at adapting the tools they have. And so I don't think people necessarily think of it unless kind of directed to do so.
That makes perfect sense. Yeah, I know we've seen one study that somebody basically solved their problem in Monty and then just pushed it out as a spice kernel and dropped it into Copernicus. But yeah, I'm just curious about that. One other thing I was curious on in OpenMDAO's pseudospectral, I'm assuming, but I have to ask ever since I started reading into how Dido does things, or at least tried reading into it, are you having users supply their own initial guess for pseudospectral, or is it doing some sort of initial guess generation?
So it is the same that it was in Otis, where basically you give it an initial guess, and for the most part, we can get away with linear interpolation. So if you can, for a phase of the flight or a phase of the trajectory, give the initial, state, the final state, the initial altitude, the final altitude, it will guess a linear interpolation of that, which is generally a horrible guess. And that Dymos is more reliably convergent with that, just because of the better derivatives and things like that. But we also have the ability to take a previous solution and load it in and seed with that, and that's still do it. And I know Dido claims free guess-free trajectory generation. I have not looked into how they do that, just basically because that hasn't been a priority for me, and that's something that we need to improve a little bit. The way we do it in Dymos right now is we can be a little how we get that initial guess generation, because you need only for things like your states and your controls. You can get a guess of your controls and the corresponding state histories and things like that. But if your the equations of motion being integrated have these implicit states under the hood, then you sort of need the values that they undertook when you last converged the system in order to make sure that those solvers under the hood can converge. You can play around with their ability to take a guess and finagle it there. But really, we kind of need all of that information, and so we're within the next month or two, I hope we have that finished in Dymos, just so that I can take a previous solution, interpolate it onto a new grid, so that and then and then run with it and be really reliable that way. I have not played with Monty. That's something that I need more experience with. Used Dido other than reading the manual for it and things like that.
Awesome. Yeah, cool. Thank you. I was curious about that. Just, the Lagrange multipliers are darn good at finding things as long as they have some initial guess. But the aura of mystery around Dido's claim of not having user supplied initial guess has eluded me for a while. Yeah.
No, I totally get it. It's I don't know what they've done, but it's impressive.
Yes, man, we could talk offline, I'm sure. It's got to be something with once you have defined co-states, right? But that's
well, and that's another thing. So they are really rigorous in how they define their problem. I like Otis and now Dymos are not as rigorous in how you define the problem. You don't have to specify your Mayer term and your Lagrange term, because your average systems analyst, your average trajectory analyst might not know that coming out of undergrad, right? So it's I try to provide a way of doing it that's a little more just kind of basic and intuitive. But then you lack the ability to do more advanced things like that, and you also kind of get enough rope to hang yourself with, because it makes it easy to pose problems that aren't necessarily, I can pose a trajectory optimization problem that's not well posed and then blame its inability to converge on the tool. When in reality the problem's the way that problem's posed.
Totally. I'm so sorry, that spawned my last question, I promise. Is there a checker for divergent solution spaces? So if an undergrad that is new to optimization defines, like, by definition, a divergent space. Is there a quick check for that or no?
No. We have a few checks in there as far as, hey, you have this constraint and it doesn't look like any of your design variables can impact that constraint, but by looking at the Jacobian matrices that we have. So that helps a bit, but and we try to make as many tools as possible because, like we said, you can set up really complex problems with OpenMDAO. So we've been trying to expand our tool capability and just like to let users manage that complexity better, because that's kind of like that's the wall that we're bumping up against right now. We're no longer bumping up against the
Awesome. Thanks so much. I promise I'm done now.
Thank you.